Now children, I am going to explain very important part in this chapter, and the topic is abnormal molecular mass or abnormal molecular weight. So you know the meaning of abnormal. Abnormal means anything which is unusual. The results are unusual in some cases. During the use of colligative properties method, sometimes there is abnormality in the results. There is abnormality in the values, and this is called as abnormal molecular mass. So see first definition. So it is defined as during the determination of molecular masses by colligative properties method. So it is condition that during the determination by colligative properties method there is abnormality in the results. There is abnormality in the results. It's called as abnormal molecular mass. So it is the point that there is the abnormality in the result during the determination of molecular mass by colligative properties method. So you know there is different parameter, like we have the depression in freezing point, we have elevation in boiling point, we have osmotic pressure, and so these are the certain conditions and under which the results are abnormal. So basically we will see the reason. What is the reason behind it? So first we will see the reasons. What are the reasons? So children, there are only two reasons. First is the dissociation of salt or electrolyte. Either the electrolyte is dissociated, and as a result the colligative property result is affected. So this is the one reason. Now second is either association. So these are the only two reasons: association of salt or electrolyte or solute. You may say here solute. So there is the either dissociation, and so you know why the results are affected, because colligative property method requires the number of moles of particles, and so when the number of moles are affected, number of moles are changed either by dissociation of electrolyte or solute or by association of solute, and so what happens? The results are going to be abnormal, and this is the reason behind the abnormal molecular mass. Now see how we can explain further. Coming to our reason, how the results are affected. See how? So here dissociation is the point, dissociation of solute, dissociation of electrolyte. Now take the case here. I am taking the simplest example, sodium chloride. So sodium chloride on dissociation or in solution, what happens? It is split to sodium and chloride ion. So here see, here we have 1 mole. And here what about? Here we have 2 moles. So here the number of mole, here n is equal to 1. Here n is equal to 1. Here n is equal to 2. So you can imagine how the results are going to be affected. Now coming to some other example, see, very interesting. Let's take the case of aluminum sulfate. Aluminum sulfate. See, this is what? This is 1 mole. This is 1 mole. N is equal to 1. N means number of moles before dissociation. It is equal to 1. So what happens after dissociation or in solution, when we dissolve in water, what happens? We have the number of moles. See, aluminium 3 plus sulfate 2. So here, see, we will balance. So here there will be 3 moles of sulfate and 2 moles of aluminium ion. So here we have how many moles? 3 plus 2, 5 moles. And what about N? N is equal to 5. So this is the reason behind the association, or this is the reason behind the dissociation of electrolyte. Now coming to second point, this association. Children, in some cases there is association of solute molecules. Solute molecules are associated. There is the bonding between the solid molecules. Solid molecules, they are joined together. Like we take the case of any organic acid. Say, take the case of acetic acid. Here we have the 2 moles. Here 2 moles. Here N is equal to 2. Now see what happens. After association, in solution, you know there is the hydrogen bonding. You have read hydrogen bonding. So see how this is 1 mole and other mole. This. And so see, there is the hydrogen bonding. This is hydrogen bonding, this is hydrogen bonding. And so what happens? Here mole is equal to 1, or we say N will be equal to 1. So this is the reason behind the explanation about the abnormality in the molecular mass. Now we'll move to the calculation part, how we apply this. Actually, children, it is rather there is a problem. This method is not foolproof. So we have to devise some mechanism how to solve out this problem. And it is solved by introducing a factor called Van 't Hoff factor. Van 't Hoff factor. Name of scientist Van 't Hoff. See how. Children, so far we have seen the abnormality and how the abnormality in the value of the molar mass is affected and the reason behind it. Now we'll see how it can be removed. So children, the abnormality in the result can be improved by introducing a factor called as Van 't Hoff factor. It is represented by a small I. And so Van 't Hoff is the name of scientist and who introduced this factor. And so it is a way, it is very simple way to remove the abnormality in the result. So it is a value. So it is a value obtained using the molar masses calculated means theoretical and observed the colligative properties observed and calculated, and so it is able to explain the nature of electrolyte. It explains the nature of electrolyte. Nature of electrolyte are explained using Van Hoff factor, and so this actually this can be expressed in two ways. And first, this colligative properties and this molar masses, they are inversely related, as you have seen in the cases, and so it can be expressed like this here. So children, it can be represented, this I, Van Hoff factor, it can be represented in two ways. It can be represented in two ways. And so this is, very much important to note that it is observed colligative property. Observed colligative properties upon normal or simply theoretical CP, means we obtain by adding the molecular masses or from the standard table. This is what, this is in terms of the colligative property, or it can be used as the normal or calculated, normal or theoretical molar mass. Normal or theoretical molar mass, like we add atomic weights. And so this observed molar mass. Observed molar mass means which we obtain by the experiment. So see, this is the point. Now how we can introduce this? So it's very simple, children. Like we have delta TB. Delta TB is equal to KB into M. So simply we introduce this. So delta TB is equal to I KB M. This is one. Similarly, delta TF is equal to KFM. So or it can be written as delta TF is equal to I KFM. Similarly, in case of the osmotic pressure measure, so pi is equal to CRT, or we write pi is equal to ICRT. So these are the simple means, these are the simple ways. This factor, this is used, and so we can remove this abnormality in the result, and so we have the values. And so simply count the number of particles before association and before dissociation, or after association, after dissociation, and so these are the ways how we have the values of this abnormal molecular mass. The last portion, children, in this is you might be knowing that during the association or dissociation there is something exactness required and needed, and so we have to see the this degree of association or degree of dissociation alpha. So you have to see the relationship between I and alpha, from your previous class. So I, Van Hoff factor, and alpha is degree of association or degree of dissociation. So very simple, this alpha is equal to I minus 1. Alpha is equal to I minus 1, and it can be this upon n minus 1. And so you know I is Van't Hoff factor, and n number of moles of solute. It is number of moles of solute. So it is number of moles of solute originally present. Number of moles of solute originally present means before association or dissociation. So like say here, if we take the NaCl, so here it will be there Na plus Cl. So here N refers to this, so here N is equal to 1. Similarly, in case of the acetic acid or formic acid, here we have this condition, and here we have the and this is. So here N is equal to 2. So this is the very logical part to note, and so we are able to have the value of the removing the abnormality in the result.